Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about a module, Mathematical Properties of Linear Vector Spaces, under the paper Quantum Mechanics 1. So students, let us see what all we are going to learn in this module. Firstly, we learn the elementary mathematical properties of linear vector spaces. Secondly, we'll define the inner or the scalar product and the norm of the vectors. Thirdly, we'll get to know the orthonormality and the linear independence of vectors. That is, what is the orthonormality condition and what is the condition for the linear independence of the vectors. Fourthly, we'll define the basis and the dimensions of a linear vector space. Then we'll learn the concept of completeness, that is, the closure property with respect to the linear vector space. And then moving on from there, we'll get to know the terms convergence sequence and the Cauchy sequence and see how the sequence converges for the vectors. Finally, we learn the condition for completeness of a vector space. Let us look at the formulation of quantum mechanics. The formulation of quantum mechanics started with two different mathematical approaches. One of the approaches was that which was taken up by Schrödinger. Schrödinger's formulation basically is the so-called wave mechanics formulation, in which it is based on the de Broglie hypothesis of matter waves, and the matrix mechanics due to Heisenberg, which is the second mathematical approach. It was shown by Dirac that these two different formulations, that is the one that was done by Schrödinger and the other one that is due to the Heisenberg, that these two different formulations in fact are special cases of a more general abstract formulation in terms of vectors in the Hilbert space, the concept introduced by von Neumann in order to present a rigorous mathematical basis for the theory. In this module, we develop the necessary mathematical background and introduce the underlying properties of linear vector spaces. So basically, we are building the various tools that we will be using as part of the mathematics to understand linear vector spaces. Orthonormality. Now we define the norm of a vector. The distance between two vectors A and B is defined by the norm of the vector, which is given as norm A minus B is equal to bracket open within brackets A minus B and its scalar product with again A minus B bracket close to the power half, which means that the norm of a vector or the distance between two vectors A and B is defined as the square root of the inner or the scalar product of the difference between the two vectors A minus B. The norm of vector A is the distance from the null vector, that is the origin. So norm of A is equal to the square root of the scalar product of vector A minus null vector and vector A minus null vector, and is equal to the scalar or the inner product of vector A with itself whole to the power half and should always be greater than or equal to 0. Next, we come on to the condition of orthonormality and linear independence. Once we have defined the norm of the vector, then we can come to a unit vector which is defined as a vector which has a norm unity. For any given non-zero vector, a unit vector can be obtained by dividing the vector by its norm. For example, if we have a vector A and its norm is within moduli A, then we can define its unit vector u as u is equal to vector A divided by the norm of vector A. The vector u is then said to be normalized. If we have two vectors A and B, then the two vectors are said to be orthogonal if their scalar product is 0. That means that if the scalar or the inner product of the vectors A and B is equal to 0, then the two vectors are said to be orthogonal. Linear independence. Now we will discuss what is meant by linear independence and how this condition is obtained. For this, let us consider unit vectors u1, u2 and so on till un that form an orthonormal set. That means that they form an orthonormal set if they are mutually orthogonal, or in other words, the unit vectors u1, u2 and so on till un are all mutually orthogonal, then such a set of vectors forms an orthonormal set. Mathematically, this can be defined as that if there are two vectors ui and uj, then the scalar or the inner product of the vectors ui and uj is equal to delta ij, where delta ij is 0 for I not equal to j and is equal to 1 for I equal to j. The set of vectors are said to be linearly independent if none of them can be expressed as a linear combination of others. This condition is mathematically expressed by saying that the equation summation j going from 1 to n Cj into Uj is equal to 0 cannot be satisfied except when Cj goes to 0 for all j. Here Uj is the unit vector and Cj is some coefficient. Thus, what this condition means is that unless and until all the coefficients going from 1 to n go to 0, the above condition is not satisfied. Then such a combination of vectors is said to be linearly independent. Further, given a set of n linearly independent vectors, it is always possible to form a set of n orthonormal vectors, which can be done by using the Gram-Schmidt orthogonalization procedure. Now, students, we'll understand what is meant by the terms basis and dimensions for a linear vector space. A basis for a linear vector space is a set of linearly independent vectors that spans the space. For example, in an n-dimensional linear vector space, a set of vectors v1, v2 and so on, vn is said to span a linear vector space if any vector in the space is a linear superposition of the elements of the set, which is given by the mathematical equation summation over I going from 1 to n ai vi. In the case of linear vector space, a basis plays the same role as a coordinate system has in the case of a physical space. Then the expansion coefficients xi can be regarded as the components of x along the vectors vi. It is advantageous to know an orthonormal basis since in this case the expansion coefficients xi in the expansion x is equal to summation over I going from 1 to n ai vi. Completeness or the closure property. Let us define the expansion x is equal to summation over I xi ui, where ui is the set of unit vectors and xi are some coefficients. Then we can define a set of coefficients xk, and these can be found by just taking the scalar product of x with the unit vectors uk. Mathematically, this can be written as the scalar or the inner product of vector uk with x is equal to summation over I xi into the scalar product of the unit vector uk and the unit vectors ui, and this is equal to summation over I xi into delta ik, and this is equal to xk, where delta ik is equal to 1 for I equal to k and it is equal to 0 for I not equal to k. The product of the two vectors x and y is given by the scalar or the inner product of vector x and y is equal to the scalar or the inner product of summation I xi ui and summation k xk uk, which is equal to summation over I and k xi star yk into the inner or scalar product of vector ui and uk, and this is equal to summation over I xi star into yi, where ui and uk are the unit vectors and xi and xk are the corresponding coefficients of ui and uk respectively. Then we come on to the completeness or the closure property. A set of orthonormal vectors ui n in a linear vector space is said to be complete if any other vector capital X in the space can be expanded in terms of the elements of the set. Mathematically, this is given as capital vector X is equal to summation I going from 1 to n xi ui, where ui are the set of unit vectors or that are orthonormal and xi are the corresponding coefficients, and where xi is given as xi is equal to the inner or the scalar product of the orthonormal vectors ui and vector capital X. It follows that x is equal to summation I going from 1 to n ui into the scalar product of vector ui and capital X vector. This equation can be considered as a criterion for the completeness of the set uin. Convergence sequence and Cauchy sequence. Definitions and concepts. Now we will investigate the rules for convergence of a sequence and that such sequences are defined as Cauchy sequence. So the sequence of real or complex numbers xn is equal to 1, 2, and so on, is said to have a limit point x if the modulus of x minus xn tends to 0 as n tends to infinity. The sequence is then said to converge to the limit x, or mathematically, the set of complex or real numbers xn, which is denoted by xn within curly brackets, tends to the point limit x as n tends to infinity. The limit point of a convergent sequence is unique, but the limit point of a sequence is not necessarily a member of the sequence. This can be understood through an example. Let us consider the sequence 1 by n, which is given as within curly brackets 1 by n is equal to 1, 1 by 2, 1 by 3, and so on. This sequence converges to the point 0 as n tends to infinity, but 0 is not a member of the sequence that we have just considered. Now, the sequence xn, that is xn within curly brackets, is called a Cauchy sequence if the modulus of xn minus xm tends to 0 as n and m tend to infinity. Every sequence which converges to a limit is a Cauchy sequence. Extending these definitions to vectors. Now let us extend the definitions of convergent sequence and Cauchy convergence sequence to vectors. So, the limit point of a sequence of vectors and a Cauchy sequence of vectors are defined in the same way by simply replacing the numbers xn by the vectors xn, and the absolute value of the numbers xn minus xm is then replaced by the norm of the vectors, vector xn minus vector xm. As an example of the Cauchy sequence, let us consider a sequence of vectors psi n. Then the sequence of partial sums can be defined as psi n is equal to summation k going from 1 to n ak phi k, where ak are the numbers and phi k are square integrable orthonormal functions. The function phi k x of a continuous variable x are square integrable if integral with limits going from a to b modulus of phi k x whole square into dx is less than infinity, where a is less than equal to x is less than equal to b. The functions are orthonormal if integral a to b, that is integral with limits going from a to b, phi star kx phi lx dx is equal to delta kl, where delta kl is equal to 1 if k is equal to l, and delta kl is equal to 0 if k is not equal to l. The functions are thus orthonormal if the above condition is satisfied, which is that the functions are said to be orthonormal if integral with limits a to b phi k star x into phi lx dx is equal to delta kl. Now, when the condition, the square of the norm of the Cauchy sequence psi n is equal to summation k going from 1 to n modulus of ak whole square is less than infinity, is satisfied, then the sequence psi n is called the Cauchy sequence of vectors. Now we come on to the condition for the completeness of a linear vector space. So, with the basic preliminaries that we have defined earlier on, we are now in a position to state the condition for the completeness of a linear vector space, that is, a linear vector space is complete if every Cauchy sequence of vectors in the space converges to a limit vector which is also in the space. So students, let us summarize what we have learned in this module. So we started with the elementary mathematical properties of linear vector spaces. That is, we defined the elementary mathematical properties of linear vector spaces, namely addition, multiplication, and we saw that in terms of addition as well as multiplication, the linear vector spaces follow the associative property, the commutative property, the identity property, the null vector property, and the distributive property for multiplication. Then we defined what is the scalar or the inner product and how do we calculate the norm of vectors. And using the scalar or the inner product, we were also able to define various other conditions that are existent in terms of the linear vector spaces, which further help us to define our linear vector spaces. Then we also learnt about the orthonormality condition and the linear independence of vectors, and we discussed in detail how these conditions are obtained. Then we went on to define the basis and the dimensions of a linear vector space, and we realized that the basis of a linear vector space is the same as the coordinate system of a Cartesian coordinate space. After that, we learned about the concept of completeness, which is also known as the closure property, and discussed this with reference to the linear vector spaces. Then we moved on to discuss the terms of convergence sequence and the Cauchy sequence, and we defined and deliberated upon the conditions which define the convergence of a sequence and when a sequence can be called a Cauchy sequence. Finally, we learned the condition for completeness of a vector space. Thank you.